Membrane evaporation is commercially employed for separation of water-alcohol mixtures. The membrane layers could be constructed of zeolites such as DDR, chabazite, faugisite, LTA, or ZIF8, even copper BTC. The membrane fluxes of water and alcohol are governed by both mixture adsorption equilibrium and intracrystalline diffusivities of the guest molecules, water and alcohol, through the microporous crystalline layers that are typically less than about 50 micrometers in thickness. In this presentation, we examine the characteristics of the adsorption of water and alcohol in such microporous materials. The aim is to stress the possibility of molecular clustering due to hydrogen bonding. In these 6 graphs, I plot the unary isotherms for water, methanol, and ethanol, indicated by the red circles, green squares, and blue triangles for 6 different microporous materials: chabazite, DDR, ZIF8, all silica faugisite, all silica LTA, and copper BTC. All the isotherms have been determined using configurational bias Monte Carlo simulations at a temperature of 300 Kelvin. For all host materials, we note that the isotherms for water in particular have very steep characteristics. For example, you see a steep rise in the loadings of water for chabazite, DDR. Indeed, for all host materials, we see that the isotherms for water are particularly steep. And we ask the question, what causes the steepness of the water isotherms? To gain further insights into the unary isotherms characteristics, let's focus on the unary isotherms in DDR zeolite. DDR consists of cages that have a volume of 278 cubic angstrom. Each cage is separated from adjacent cages by narrow 8-ring windows whose dimensions are 3.8, 3.6, 4.4 angstroms. The unary isotherms are plotted here, and to gain further insights, I calculate from the unary isotherms the inverse thermodynamic factor, 1 divided by gamma, which is defined as the partial of ln q, q being the molar loading, divided by the partial derivative of ln f, which is f is the partial fugacity in the bulk fluid phase. For the simplest case, in which the unary isotherms are described by a single site, a Langmuir isotherm, 1 divided by gamma is equal to 1 minus theta, where theta is the pore occupancy. In other words, 1 divided by gamma can be identified as a parameter that quantifies the vacancy. So we take these unary isotherms and determine the 1 divided by gamma for each of these isotherms by differentiating the isotherm fits, which are described by the dual Langmuir-Freundlich model for each of the guest molecules. The values of 1 divided by gamma are plotted against the pore occupancy. In this graph, we note that for methanol and ethanol, 1 divided by gamma decreases with increasing pore occupancy. In other words, the vacancy reduces with increasing pore occupancy, as one should expect. But the behavior of water is completely different. For pore occupancies less than about 0.3, we note that the inverse thermodynamic factor increases in value to about 3.2 before it finally reduces to 0. Now, how do we interpret a value for the vacancy that is larger than unity? This seems to be incredulous. Let us examine this a little bit further in the next slide. In this graph, I plot the inverse thermodynamic factor for water in 5 different host materials: faucesite, LTA, chabazite, DDR, and ziphate. For all 5 hosts, the 1 divided by gamma factor has values exceeding unity for pore occupancies below about 0.3. So let us try and explain this by means of a checkerboard representation of the number of sites available within a microporous crystalline adsorbent material. I consider 2 cases. On the left-hand side, I have a checkerboard with 64 available sites that are occupied by 10 unclustered molecules represented by these red circles. So the occupancy is 10 divided by 64. Let's now consider a scenario in which we have molecular clustering. Say in the case of water, this clustering could be due to hydrogen bonding between the pairs of water molecules. And let's assume that the adsorption of water is represented as the adsorption of dimers. So if these 10 molecules are all clustered, then the clustered species, each of the 2 molecules cluster together, and this dimer will occupy 1 adsorption site. So if cluster formation occurs, the occupancy, pore occupancy, is 5 divided by 64. In other words, 59 vacant sites are available for further adsorption. even if no further clustering occurs, and additional water molecules do not cluster, then a simple arithmetic would lead to the conclusion that we can additionally allow the occupancy of 59 additional water molecules. So 59 plus these 5 sites, these 5 sites are occupied by 10 molecules, so 59 plus 10 is 69. So if there's cluster formation, I can allow 59 plus 10 equals 69 molecules to occupy 64 sites. In other words, if clustering occurs and I have only 5 dimers and 59 monomers, I have 59 plus 10 guest molecules, that is equal to 69 molecules that can occupy 64 sites. In other words, the vacancy is effectively increased due to cluster formation. So the conclusion we draw is that 1 divided by gamma is a measure of the effective vacancy, and values exceeding unity signify the occurrence of cluster formation. And this leads to steep isotherms. Put another way, steep isotherms for water are caused due to molecular clustering, in this case hydrogen bonding between pairs of water molecules, and this leads to an increase in the effective number of sites that are available for adsorption. In a follow-up presentation, whose name is Cooperative Mixture Adsorption, I demonstrate that molecular clustering and hydrogen bonding results in a phenomenon of cooperative mixture adsorption.